So we have
mass of M of a spring oscillates with a frequency of 0.83 hertz. Okay, when an additional 780 grams mass is added to M, the frequency is 0.61 hertz. What is the value of M? Okay, so
the way that I had it set up. I was. Do we have to find the we have to find the spring constant, right, K, for this problem?
no? Yeah, I think so.
So, like, cause the way that I was setting it up, like I had two variables that I was solving for. I was solving for K and for M.
Yeah.
And I didn't know if there was another formula that I could plug in for either K or M.
Let me think. Well, I know for K, you can solve it using Hooke's law usually, but we don't know how far it stretches.
But even then,
when the mass is added.
Wouldn't you still have two variables if you use Hooke's law? Because you have the 780 M and the K that you're solving for.
Yeah. Oh well. Yeah. So I was saying with Hooke's law, you could solve for using a separate equation, solve for K, and then plug it in. So like you'd use this equation.
Yeah.
Solve for K.
Yeah.
And then plug it in.
So.
But the only thing is we don't know what X is.
Yeah. Yeah.
So I think let's see here. Oh, I know how. Okay, so you could set it up like this. So we have our frequency, right? Equation.
Yeah.
So 1/2 pi square root of K over M, right? So okay, so our initial situation is we have a frequency of what is it?
83 hertz for.
Okay, yeah, 83 hertz.
Yeah.
Okay, cool. So 83 hertz equals 1/2 pi K over mass, right?
Yeah.
Yeah, it's like okay, well we have two unknowns, can't really solve for it, right?
Yeah.
So what's the second situation? What was the change in frequency? What was the frequency?
The new frequency was 0.61 hertz, and you added 780 grams.
Okay. Oh, this one was 0.83.
Oh, sorry.
No, you're good. 0.61 hertz. And now we have mass plus 0.78, was it?
Yeah, 0.78.
Okay. So this is our new situation now, right?
Yeah.
But we still have two unknowns?
Yeah. Yeah,
okay.
I was getting this far and I didn't know
okay.
what to do.
So what if we take this equation right here and we solve for K, right?
Okay.
So if we solve for K, well, let's just do that real quick. So it's going to be 0.83 times 2 pi, right?
Okay, yeah.
So times 2 pi equals square root of K divided by M. Square that to get rid of this. So square all of that. And then we're solving for K. So we want to multiply by M to get K by itself. So you could plug that in if you wanted to solve for something. So it'd be like 0.83 times 2 pi squared.
Okay.
And then you'd get some number times M.
Uh-huh.
What if we plug that whole thing into here, right? Then the only thing we have to solve for then the only variable we have is M in this case. And we can solve for it.
Okay. Alright.
Yeah. So yeah, it's just mostly a bunch of math, like at this point, like yeah. How's it going, Zach?
Good. So on this one, I looked back here and it said start out like this. I'll let you read it.
Okay, so an object of unknown mass, M is hung from vertical spring of unknown spring constant K. First, the object is given a slight push upward to execute. Okay. Determine the period of the oscillation. Okay. So I guess we need to solve for the spring constant is what?
Yeah.
Because we don't have it, right? All I know is it stretches that much, and it's the force. We don't have the force either. Because it just says mass.
We don't know anything. Seems like.
All it tells you is 0.14 meters. It's deserved to be at rest when the string stretches. Yeah, because then you have an unknown, huh? Because it'd be like mass times gravity equals like the 0.14 times k. So it'd be like k equals something times mass, basically, right? Well, you could plug it into, actually, you could probably plug it into t then. K, and then mass would just cancel.
Yeah, that's what.
Is that what you tried to do?
But why is it kx initial minus mg? Why is this the sum? That's what it was saying.
Calculus.
Like, I understand how they solve for k and everything.
Oh, they just wrote it down. Like, this is what, so it's Hooke's law equals k times this, right? Well, all they're doing is they're just saying the force on it is mass times gravity.
What about the negative that's out front?
So, well, that's just because they subtracted to this side to get this. I think that's what they did. And then they just solved for k. So k is, well, I don't know why they did that. I would just.
Wouldn't you have? But isn't there a negative out in front of k? So you'd have to divide by negative change in x.
Yeah, but like since you're talking about like a spring going down, a lot of times when you talk about Hooke's law, like it's gonna be a negative force anyways because it's pulling downward.
Okay.
So like remember, like most of the time a positive force will be
Right.
upward, negatives downward. So this should just be like,
So they're just assuming that force is negative.
yeah, so
Because
like
gravity
this
would be
positive. Well, you have to subtract it anyways now. Well,
Just leave it
why
up there
even do
and
that?
divide by.
Yeah, why would they even? Yeah.
Okay.
Yeah. So yeah, that's kind of weird. And like a lot of times you could reason that k, like you don't really have a negative k ever. So like, yeah, I'm always confused why they put that negative there anyways. Because usually the force is negative anyways, so it's just positive in the end. But yeah, the way they wrote it there is just stupid. I'd just do it this like
Yeah.
whatever
That
makes
makes
sense
more
to you. Yeah.
Okay. And then you can just plug in.
Yeah, and then the mass should just cancel.
Real quick.
Okay.
For the 0.83 2 pi squared up there, do we square both 0.83 and 2 pi, or do we multiply those together and then square that answer?
It shouldn't matter. I would square those together. I'd multiply those together.
And then square it?
Yep, because that's the first step is you multiply by 2 pi.
Okay.
And then you square, yeah.
Okay.
Yeah,
So,
what'd you get for that?
like this? Is that?
Yep, that looks good.
Okay.
Yep. And you plug that in for here, and that's multiplied by m,
Yeah.
that number, so like 27 times m. You plug it in there. Then you slowly solve for n,
Okay.
basically.
Okay.
Yeah.